Thank you. So this is joint work with Nicolas Tabareau, with whom I'm doing my postdoc. And just to tell you, if you've read the abstract, then the story is going to be slightly different because this has evolved since the time we submit this. Okay, so I think that everyone here must know what inductive types are. So when we specify an inductive type, we specify a list of generators, but this talk is about quotient inductive types, in which we also specify equations. So for instance, we have the quotient inductive type of finite multisets, which is basically the type of lists to which I add the equality constructor saying that I can permute the elements of the list. Of course, I need to ensure that this type is an H set for it to be a quotient inductive type, but actually in this talk, I will only consider theories with UIP, so I'm not including a specific constructor saying it is an H set. And just like when eliminating a regular inductive type, we need to specify one case for each constructor. Here, we also need to specify one case for the equality constructors, which will basically ensure that the function we are defining respect quality. So then if we're defining a function that sums all of the elements of the multiset, then this will work because, of course, addition is commutative. Okay, so why can't we have then quotient inductive types in our favorite proof of systems like Coq and Rock and Agda? Well, the problem is that if we take the equations that we get from the definition of the QIT and we do a match on it, well, this equation, this axiom is in normal form. So this match will never reduce. So it's stuck on this equality proof. And we break canonicity. So the equality axioms, they can block computation. And this is why we'll shift the focus to Altenkirch and McBride's observational type theory, in which equality instead defined, eliminated, using a cast operator. And the real crucial property of OTT is that the computation rules for cast will never look inside equality proofs. So this is the rule for when you have a product type. And basically what you do is that you start from this proof that A times B equals A prime times B prime. And the important property of OTT is that from this equality proof, you can extract two proofs that say that A is equal to A prime and B is equal to B prime, which is something that, of course, you cannot do in regular type theory. And from this, you can continue applying the cast to the components of the pair. So then you never ask what is the shape of this equality proof. And because of this, we can, OTT is a perfect setting for extending the theory with equality axioms that we know will never block computation because we never ask what is the shape of an equality proof. So we can get an X, prop X, then quotient types. So this work is about work in progress, meta-theoretic justification of non-indexed QITs in OTT with dependent eliminators that compute definitionally. So this is an important point for me, which is one of the differences with the prior work. So there are a number of plans that we consider. We can think of the idea of just extend OTT with a QIT scheme and study the meta-theory of this. But of course, inductive schemes are very big beasts, and you have lots of vector notation, and this is not a nice thing to manipulate formally. So instead, it's a bit better to try to reduce QITs to something that are more basic. And the first idea would be to do this from inductive types and the quotient type. But, well, there are two problems. So first, for infinitary QITs, there are some counterexamples that show this cannot be done. But even for the finitary one thing that I didn't hear very much is that even if you try to do this construction, at least the construction that I know of, the eliminator will not have the definitional beta rule. So because I have this criteria that I want them to compute definitionally, then this will also not work. So instead, the approach that we take is that we extend OTT with Fiori et al. QW types, which are kind of like a universal QIT. And then to prove that all QITs can be constructed from QW types in OTT. So yeah, this is the approach that we take. Well, if you look at their paper, actually the construction is claimed by Fiori et al. in extensional type theory. And they even give a scheme for QITs, but actually they do not proof, really. They give a couple of examples of how it can be done, but they actually don't even construct the eliminators for the example that they give. So this is one of the gaps that we want to close with this work. And one of the main motivations to do this is that in the future, so there's this observational version of ROC that was started by Loic. I don't know where he is, but and one of the ideas is that we would like to extend this version of ROC to have a primitive schemes for QIT so that users can have access to this. So this would be a justification for doing this while knowing that you're not breaking the meta theory. Okay, so this is the plan. So we want to we start with a QIT scheme, and we want to be able to construct the corresponding QITs from QW types. So let me start then by saying what are QW types. So we first start with this definition of what is a signature, and this is the same notion that we have on W types. We have a type of operations, and for each operation we have a type representing its arity. And then we need to bootstrap the construction of QW types. So we define this, which is basically the W type, but over which we add this variable constructor over this type gamma, which is now a new parameter of the type. And the OP constructor is just the regular constructor from W types. And the idea is that once we have this, we can use this to specify the endpoints of the equality of the QW type. So we then are able to define the notion of equational theory of a signature, which will be a type of equations for each equation, a type of representing its context. And then we have the left and right-hand sides. And this is where we need the QW bar type to express these two endpoints. And now we're finally able to define the QW type, which parameterizes over a signature and an equational theory over that signature. So we have the up constructor, which is the same as the QW bar and W types. But then we have the equality constructor, which takes for every equation, and this little gamma, you should see it as a substitution that is defined over the context of the associated equation and giving you an element of the QW for each element of the context. And then you apply the substitution to the two endpoints of the equality. And the substitution function will be then defined by induction over the QW bar here. So this is the Marcello Fiore et al.'s QW types. So this is what we're going to use. And okay, so this is the plan. But the problem is that the construction, well, it's not exactly hard, but it's very tedious because you need to change, because QW types, like W types, they have this higher order way of representing the arguments of the constructors. And you need to do this change of representation when you're constructing each QIT. So this is a bit tedious. So what we instead do is that we introduce a type in the middle, which is a modification of the QW type, but which is more first order. So the idea is that we do the hard part of switching the representations between higher order and first order like once to construct this type. And then we can construct QITs much more easily from TM, because then the arities, the recursive arguments are already represented in a way that we want. So let's see what I mean by this. So this is the QW type that I just showed you. And we see that the parts which I don't like are in red. So what we're going to do is that we're going to change here the notion of arity to take a natural number. And then the way that we're going to represent the recursive arguments of each constructor is through a nested use of a vector. Now, this will be, of course, only a finitary universal QIT, but this is just to simplify the presentation here. You can look at the GitHub repo, and there's the infinitary version in which instead of taking a net, you take a list of types. And yeah, so this is the type that we want to use in the middle of the encoding. Okay, so this is the plan. So we have the A constructor and the construction A, which is TM from QW, and B, which constructs every QIT from TM. So for the A part, so in OTT, we've showed that we can construct TM from QW, and OTT extended with actually this rule, which is part of the original definition of OTT, which allows you to eliminate identity casts even when you're stuck on the type, when this type A is a variable. And actually, this is fine because on their last work, Puget and Tabareau showed that we can extend the occasional theory with this rule, and this does not break any like this ability of conversion still holds. And this was actually done in the observational branch of ROC. So this is why we have this new ROC symbol here. And the proof, like I said, it's a bit tedious because we need to switch between these different ways in which we're going to represent the branching of the constructors. But the whole point is that we only need to do this once, and then we can go to the second part, to the construction view, which is still work in progress because I still have to write formally the QIT scheme and write the construction on paper. But I've already have some examples that you can see in the GitHub link that is in the abstract that suggests that this is direct because, like I said, we already have the type, the representation that it is more convenient. Let me also say that, a possible question that we could have in this situation is, I mean, if TM is more convenient to use, why do we still have QW at the end? And the reason is that, I mean, TM is still like a more complicated type to write because you have like this nested occurrence with VEC, and in the finitary version, it becomes like a nested occurrence with this all combinator over lists. So I think that QW types are more easy to manipulate, to do the meta theory, but then you can use them to construct TM, which is easier to use. So this is just an example of like how the reduction work. I don't expect you to read, but just going to tell you that the thing that you should see is that you do not use transport anywhere when you're doing this reduction, well, except on the type of the eliminator, but this is you cannot do without it. And this would be different if you were doing this construction directly with QW types. So this is like this justifies, like exemplifies what I was saying by saying that it's easier to use TM. Okay, so we have a work in progress construction of infinitary non-indexed QITs with definitional beta rules in OTT plus QW. Of course, the next step is to make sure that the meta theory of OTT plus QW is indeed well behaved. We expect it to be, but we like to prove this. So there are a couple of steps. So first, force normalization and the decidability of conversion. The most direct way would be to do this by logical relations, to extend the logical relation proofs of Puget and Tabareau. But actually, we don't even have a proof for the W types yet, a formalized proof. So because QW types add a lot of noise in the definition, we think that this would be maybe a bit unrealistic, at least right now. So an approach that we are exploring is whether we can simulate the equality checking algorithm of OTT plus QW using just OTT plus W. So this way we have like a simpler theory over which which doesn't have the quotient part anymore. Then the second step, which might sound a bit strange, is that we also need to prove consistency. And this is strange because normally consistency is a corollary of normalization for standard type theories. But actually for OTT, this is not the case. So what we plan to do is to adapt the set theoretic model of Puget and Tabareau. And I don't expect this to be any problem because, I mean, Fiori et al., they also look at the models of QW, and they even prove that you don't even need the full strength of set theory to do a model of it. So because we just want a set theoretic model, this shouldn't pose any problem. And then we can get from normalization and consistency canonicity, which is yet a different strange point of OTT, the fact that canonicity relies on consistency. But yeah, once we have this, we can then deduce canonicity of OTT, and a formal canonicity for the constructed QITs should follow. Of course, we need to specify what we mean by canonicity in this sense, because it's not canonicity of a type in the theory, but a type which is constructed. So there are many definitions that we can think of, and for one of them, this should hold. And then for future work, of course, like I said, we would like to add a primitive scheme of QITs to the observational version of ROC, and we see this work as a justification to, like, we can do it without breaking anything. And of course, I'm only concerned with non-index QITs here, but we would like to explore more complicated classes of types in the future, such as index QITs and QIITs, which would allow to do the formalization of intrinsically typed and fully quotient type theory in, for instance, this observational ROC. And for this, I expect that the work of the session chair will be an important inspiration for this. Thank you.